Yeah, cool. All right, so today I'm going to talk, well, the title of the talk is kind of like building efficient programs with Pinocchio, but I'm going to touch at different aspects at the same time. I tried to come up with a title that would kind of like summarize everything that I'm discussing, but I couldn't. So I just settled for building efficient programs. That is the main theme, but on that topic, there is other things that we're gonna discuss as well. But before that, just going a little bit about me. So I'm Febo. I work at Anza at the dev platform team. So main contributions there is going to be on the Solana SDK, on the Solana program organization, which then encompasses many of the programs that you use every day. So the token program is there, like stake program and other ones, config program and everything. So they kind of like the ones that you consider like core programs. I somehow involved either doing some maintenance on the programs, writing clients or updating clients, updating the SDK version of these programs and so on. Then I do a bunch of work on Pinocchio, which is one of the things that I'm going to be discussing today. So more on that in a bit. And also Kodama, which if people are not familiar with, is kind of like an IDL standard that you can generate clients very easily, not only like Rust clients, you can do TypeScript clients, but also other things, not necessarily only clients you can use to do integration. So if you want to parse an IDL and kind of like consume the IDL with a different purpose than just generating a client, you can use Kodama. That is going to give you kind of like a friendly typed representation of what information is on the IDL, and then you can do with that information whatever suits your case. So are kind of like the main things that I'm involved. All right, so a little bit about the agenda of today. So I'm going to talk a little bit about Pinocchio, which is kind of like what we're going to be essentially using to write efficient programs. So go a little bit about what it is, why you should use it, and how those kind of benefits are achieved. Then I'm going to talk about two examples of where we used it and what sort of like benefits we got, which is P-token, the reimplementation of the SPL token, and PMemo is a reimplementation of the memo program using Pinocchio. And then the last slide, I have just some links with like referencing the stuff that I discuss here. Some of these parts I plan to kind of like have a demo, then I'm gonna show you some code, like discuss in more detail some sort of like the implementation. I'll be mindful of the time as well, so I'll see whether it's better to kind of like have that all at the end or have it between topics. Right now, the slides, the way that I put them are between topics, but I'm going to be mindful of the time as well to see whether it'll be easier just to bunch everything at the end. But we'll see how it goes. At any point, if people want to kind of like stop and ask things, I'm not going to have my eye on the chat like constantly. So if you raise your hand, I think it's easier because then something pops up in my screen and then I can stop. So any point, feel free to stop and ask questions. All right, so starting, I don't know how many of you have heard about Pinocchio or not, or even if you have used Pinocchio or not. But essentially, Pinocchio is a library to write Solana programs. So you could use the Solana SDK, and you can use Pinocchio. So they kind of like, we are starting the process of integrating them, but at the moment, currently, they are not fully integrated. There are things that you can use from both in one or the other SDK, but essentially started independently. And the reason that it started was that over kind of like a year ago, if you're using the SDK, it was a little bit challenging in terms of the dependencies. So using the SDK meant you had to bring lots of extra dependencies to your program, which most of the case you are not using those dependencies in your program. It's just that the way that the crates were kind of like designed, they were bringing these dependencies together, and was very easy to end up with dependency problems. And sometimes these problems didn't come from the SDK itself, was just a dependency of the SDK that for some reason introduced a breaking change on a minor version or on a patch version, and that would cascade to your program. And then every time you try to bump to a different SDK version, likely you're gonna end up with some dependency issues that you had to wait this other dependency that you were using to also upgrade, and this other to also upgrade, and so on. And sometimes you'll be like on deadlock and having to manually edit your cargo log file to kind of like pull the correct versions and everything. So this is how it started. It was a conversation with John Sink at the London Hacker House last year, like it was June. And we were talking, and then all of a sudden we were like, oh, what if we just write an SDK that has no dependencies? So right now, this is how Pinocchio works, is literally there is no external dependencies. Everything that you need is there. Everything that your program is gonna use is there. So it started with this kind of like this goal of let's try to mitigate dependency issues when writing programs. So it would be kind of like a program first library. Everything that you bring into Pinocchio, it has to make sense for programs. If it doesn't make sense for programs, it shouldn't be there. But while we were doing that, so that was the kind of the main motivation, but while we were doing that, because we were having to redefine types and things like that, then we started to take a focus on performance, because at that point we knew that things, some of the stuff on the SDK were not very program friendly in terms of performance. Things that the SDK was doing was not kind of like performant to do that on chain. There was a better way to do that on chain. So we started, when we were rewriting these types, we started then changing that implementation to make it program friendly, to follow what works best in on-chain programs. And one of the key things that we did is it uses zero copy types, because allocation of memory and copy of memory on an on-chain program is expensive. So that is one of the key things that Pinocchio does, is uses zero copy everywhere, essentially. So there is no additional allocations. As a result as well, that means smaller program binaries, because you are doing less things on chain. So one thing we always talk about like compute units, and this compute unit, sometimes it sounds kind of this magical unit, but essentially compute units is the number of instructions, like assembly instructions, that your program is executing. So the more you do in your program, the more instructions your program has in terms of like BPF instructions, the more CUs you're gonna consume. So that's essentially what it means. So if you're doing the same thing but in a simpler way, so if you're not doing allocations and not copying data, then that by default you're doing less things on chain. So you're using less CUs, but also your binaries is smaller because it doesn't have all those BPF instructions as well. So it's kind of like is a effect of having a more efficient library in terms of compute units. The effect is that you're going to end up with a smaller binary because you are doing less instructions. So that's essentially what is Pinocchio. If you had to do like in a one sentence, you would say is a program first library to write Solana programs. Why should you use it? I think I kind of like already hinted before. Is by using it, you're going to end up with a lower compute unit consumption in your program. So the program entry point, which every program has, which is the starting point of the execution of your program, is more efficient. And I'm going to show you kind of like some numbers of like what we mean by more efficient. And also we have all these build types, these zero copy types, that also saves you compute. And also I'm going to show you some numbers on that as well. And as I said, and you end up with a smaller binary. The other aspect that Pinocchio is a no STD library, so it doesn't include the STD library from Rust, which means it also contributes to have a smaller binary because it brings less things from the Rust library itself. So it uses just a subset. So the no STD is a subset of what is included in the STD. So the STD is a much bigger thing. The STD, no STD is just a subset of it. So it just depends on that subset. So it already brings less things from the Rust side as well into your program. So they'll be the two main kind of like main benefits of using it is lower compute units in a smaller binary. And at the same time, the way that you write a program is pretty much similar. I'm going to show you an example, so hopefully you're going to agree with my observation. So we're going to talk 3 points here in how Pinocchio works and how it helps you writing efficient programs. So with the program entry point that I already hinted, that is more efficient, using zero copy types. And also we rewrote the way that you log messages in your program as well, which helps saving CUs. So I think the program entry point, I believe at this point you are already familiar with it, but essentially when the runtime invokes your program, it's going to serialize all the information that your program needs. So it's going to be all the accounts that your program was invoked with, the instruction data that was sent as well, and the program ID that was called. So that is going to end up being an input buffer, just some bytes, and is just an array of bytes. That's how the runtime serializes all the information for your program. But that's very hard to work with because it's essentially just a byte array. So you don't have anything nicely typed and so on. And if you wrote a program before, you're going to see that you write your process instruction. There is a very nice kind of like signature where you get your program ID already as a pub key. You get a list of accounts as an array of account info, and you have your instruction data as some bits of bytes. But that's not how the runtime invokes a program. That is what the program entry point does for you, and then parses the information and gives them kind of like nicely divided into these little parts. And that is something that when you use kind of like your macro, the entry point macro, like kind of like what is here showing here, kind of entry point. This is the job of that macro, is breaking down this input array and extracting these 3 pieces of information here. And that, as you would expect, is going to take compute. It's not something that is for free, although it's transparent, it's not for free. And that is compute that is used even before your program logic starts, because that is something that macro does for you before your process instruction get called. So most of the time, depending on what you're using there, you don't have really control of how much compute units that part is actually consuming, and you don't have an easy way to optimize that part unless you swap it to something else. Which essentially is what then we did with Pinocchio. where we rewrote that entry point macro to be more efficient. And essentially what we did in this rewrite was we don't do any dynamic allocation in that macro. The one from the SDK, the current one from the SDK, it does allocations and it does copies as well. So on the Pinocchio side, we also don't do copies. We use those view types. So by not doing allocations, by not doing copies, we get significant improvements. So here is a little simple benchmark where the process instruction of the program is completely empty. So we are just measuring the performance of the entry point, how much it takes to parse that information and extract the pub key of the program, the list of accounts, and the instruction data. And you can see here, even just when there is one account, the SDK entry point is already using 261 CUs, while Pinocchio can use only 17. And then it scales also much nicely because even when it goes to 64 accounts, the Pinocchio entry point roughly just uses 504, and the SDK uses 9,270. So that is all the gain that is not doing dynamic allocations and not doing copies, essentially referencing that input directly. We went in a step further with Pinocchio, and we created this idea of a lazy program entry point, that instead of parsing the entry point beforehand and getting all those pieces, we essentially just wrap the entry point into a instruction context, which offer you the methods for on-demand parsing. So if you want, you can get accounts and so on. And then at that point, when your process instruction gets called, essentially nothing almost has happened. The only thing that has happened is wrapping the instruction context, wrapping the input in this instruction context, and then calling your process instruction. So this kind of like empty program here, using the lazy program entry point, then uses 2 CUs regardless of the number of accounts, because it's actually not doing anything, not parsing anything. So then it's up to your program to kind of like consume the input the way that you see fit. And this is essentially the entry point that we use for the memo program. The rewrite of the memo program uses the lazy program entry point because the use case there fits perfectly. So when we see that example, we can discuss a little bit more why it was suitable for that particular scenario. So essentially, you have even an extra control over how the entry point operates using a nicer API without having to index bytes directly. And without much penalty, because this essentially just takes 2 CUs for you to get into your program logic. So there's the first aspect that when you switch to Pinocchio, you start seeing these gains on the entry point directly. So you can see already kind of like if you on average an instruction is going to take to 4 to 8 accounts, so you can see gains already in the order like 600 to 1,000 CUs. So as I mentioned, one of the ways that the entry point kind of like saves those CUs is because it uses these view types. The view types are essentially zero copy types. And this is a very kind of like sort of like high level representation of how something that is not zero copy works and how zero copy works. This is an abstraction. This is not exactly precise. But in general, when you're using kind of like bin code or Borscht for your account data, for instance, which is like if you're using Anchor, eventually like Anchor serialize, deserialize is essentially Borscht. What happens is that when you have your account data, this is the account data that the runtime gave it to you, When you want to say, okay, I want to deserialize to kind of like use this account with this specific type that I know. So let's say this is the account data of a token account. So you're going to deserialize that account data into a token account. What is going to happen, and most of the time it's kind of like under the hood, is that there is going to be an allocation. So memory is going to be allocated on the heap. And then the data from the account is going to be copied to the heap. And then you're going to have this very nice typed token account that your program can use. So anytime that your program use or update a value in this token account, is going to be updating the value on this copy, because that's the one that the program is operating on. What happens at the very end, then, you need to copy this data back to the account data, because otherwise the data is going to be lost. It's not going to be persisted. If you use Anchor, Anchor is going to do that for you automatically. So as soon as your process instruction finishes, Anchor is going to then kind of like copy the data back to the account data, so you don't have to kind of like do it manually. If you are doing some sort of writing your program just with the SDK, what is going to happen is that you're going to have to then write this data back to the account. So you see here, there are many things happen here. You're going to have at least one allocation, one copy when you are reading the information from the account data into this allocated memory, and one more copy when you have to persist any of your changes into the account data. So you can understand that this is expensive, and this, in the majority of the cases, is what consumes the most CUs in your program, especially if you're using larger accounts. And larger, I don't mean like megabytes. I think like 200 bytes, 500 bytes is going to add usually around 1,000 CUs for you to deserialize the account data. On a zero copy style, what happens is that you essentially operate directly into the account data. So there is no allocations, there is no copies. You essentially tell Rust that, oh, this account data is a token account. And you can access then the data as if it was a token account. And if you update any of the fields, it updates directly on the account data. And you can understand, I think, just even looking at the simplicity of the graph, you can understand that a zero copy is going to be much simple. And anything that is simple is going to use less CUs, because it means less instructions that your program is going to have to execute, kind of like PPF instructions. So that's where big gains, where you can get big gains in your programs using zero copy. And zero copy is not restricted just for the account data. You can use zero copy for instruction data as well. The gains are probably a little bit smaller because instruction data tends to be much smaller, because it's usually kind of like few bytes up to kind of like 100 bytes, but depends on your program. You might get big gains there as well if you're using a large instruction data. And here is kind of like just a representation of how the account info in the SDK looks like and how the account info in Pinocchio looks like. So on the SDK, the account info is a type that has 48 bytes. Those 48 bytes have to be allocated. So when the entry point is parsing the accounts, is allocating 48 bytes for each account, and then is actually copying. Some of the fields here are references, but it's still each reference is an 8 bytes. So those 8 bytes have to be copied. If it's just, even if it's just a reference, there still has to be allocated and copied into the memory. So it's gonna copy a bunch of references and a bunch of values here. Those are like, this is essentially the same cost as copying a reference. So copying the value here doesn't matter. and these ones are cheaper because it's just 1 byte. But you still kind of like copying some like 4 references and then some other values. On Pinocchio, what happens is the account info is essentially a wrapper type just over a raw pointer to the account. And this raw pointer to the account is essentially the pointer to the input buffer that you got. So as soon as you determine here is the beginning of my account in the input buffer, you can wrap that raw pointer into an account info and say, okay, here is an account info and here is the start of the account. So that's what like Pinocchio does. And that's where you can see that you're already saving because you are just using 8 bytes to represent an account info instead of 48 bytes. So that's the idea of using like view types. Essentially use the input buffer directly as your account info instead of taking references and copying values from it and operating in this allocated memory space now to represent your account info. We also redefine not only the account info, we also redefine the account meta and the instruction. So the account meta, we uses all references. The instruction also uses all references. And the effect of that is that you get cheaper cross-program invocations, CPIs, because of that. Essentially, I broke it down the cost here in parts. So for you to understand where the gains are, some of the gains obviously is on the entry point. So to create an account, you need three accounts. So the funding account, the account they are creating, and the system program account. So this is a program that receives 3 accounts and does a CPI to the system program. So 547 is the cost of the entry point, parsing 3 accounts on the SDK, which is what I show you on the table here. So 3 accounts is 447. So that's where that's come from. 1,000 is the base cost for a CPI. So a CPI is always going to cost you 1,000. Then depends of the accounts that you're passing, you get charged an amount based on the size of those accounts, plus anything extra that you do to invoke the CPI. On the SDK, the CPI essentially is going to mean creating account metas, creating an instruction, which eventually gets cloned into the invoke before the actual syscall to the CPI gets invoked. And that is the 899 cost here. So this is the cost of like the variable data that you are passing to the CPI, plus all the extra steps and clones and allocations that the CPI code is doing on the SDK. On the Pinocchio side, you get 37, which is the gain on the entry point. The 1,000 for the base cost of the CPI is the same because that is the syscall cost. But then you only get 244 of the overhead, which majority of those 244 is the CPI charge for the size of the accounts that you're using. And there is a little bit of overhead in terms of preparing your account meta and instruction to call the syscall. But you can see the overhead is much, much smaller. So it's about like, just considering the overhead of the CPI here is roughly 650 CUs less. So overall, using Pinocchio, the entry point plus using the CPI that Pinocchio offers, you in this very simple program, you already save like more than 1,000 CUs. So those are the other benefits of using these view types, not only on the entry point, but also the CPI can be made, it can be cheaper because you're doing less allocation and less clone, like copying of data on the CPI. Okay, so we covered so far. We went over the kind of like the entry point, a little bit about the view types, zero copy. The last bit that I wanted to kind of highlight is that program logs is something that is expensive to do it. So although it's very useful to have logs in programs and so on, but they can easily kind of like add up CUs to your program very quickly. And the cost of logging, the cost of logging can be split in two parts. One of them is the base cost of logging, which is either 100 CUs or an amount equivalent to the length of the message that you're logging. So if you're logging a message that is over 100 bytes, then you're going to get charged that length. Now, if you're logging a message that is less than 100 bytes, you're going to get charged 100. So 100 is the minimum that you get charged. You can get charged more. So that is one part of the cost, is the base cost. So you can't log something for less than 100 CUs, because that's the syscall of the log is going to charge you at least that. But on top of it, there is a variable cost, which is the formatting cost, because depending on what you want to log, you're probably going to format the message. So if you want to log kind of like LUM ports, you're probably going to put like LUM ports of account X and then the LUM port values. And most of the case, what you're going to do is you're going to use the format macro from Rust, from the Rust library. But the format macro is known to be heavy. It's known to be heavy even outside kind of like a Solana program context, even kind of like on a Rust aspect. They already recognize that it's heavy. It's heavy because it's very flexible. It's kind of like you have lots of ways for you to format the message and everything. So in order for the macro to kind of like resolve exactly what has to be printed, it creates a really complex representation of the parts that are static, the parts that are formatting, and what format applies to each of these parts and so on. So I end up in a very complex memory representation of what needs to be printed. So although we cannot change the base cost, it's not something that your program has control to change, because that's the cost of the syscall. We can do something about the formatting, because if we can do the formatting more efficiently, then we can reduce the overall cost of logging messages. So essentially, this is exactly what we did when we were working on Pinocchio. So we came up with this lightweight logger type and a log macro that goes with it. Again, following similar principle, it doesn't do any allocations, minimizes copies. You can't avoid copies because you are formatting a string. So eventually you're gonna have to copy, like generate the formatted string that is gonna involve copies. But at least we don't do dynamic memory allocations and things like that. So we do as much as possible the use of static memory and efficiently try to minimize copies. And we still do include some formatting options. It doesn't have all the formatting options that the format macro offers you, but for the majority of cases, of use cases of formatting messages on a program, probably the log macro is going to cover that case. And here he's just some values just to show you. Just formatting a simple U64, printing the message LUM ports equal and the value, which involves formatting a U64. If you use the MSG macro, which is the one from the SDK that underneath is going to use the format macro from Rust, is going to cost you 100, which is the base cost of the syscall, plus 274 CUs. That is the cost of formatting the message, is actually putting the U64 in a text form in this string. If you're using the log macro, you still get the 100 CUs of the base cost, plus 13. 13 is what it costs for formatting the U64. And then so that gives you kind of like a gain of 261. So there's something here in the chat. Is it stripping all necessary formatting options and will include something that is commonly used? Is actually a complete rewrite. Is because there is no easy way to simplify the format macro from Rust. And if you click on this issue here, wrong. If you click on this issue here, if you open this issue, you're gonna see, maybe, I don't know if what I'm gonna happen if I click here. Oh, it works, okay. So if we see here, the person was trying all different ways. So this is essentially all the things that is happening underneath. As I said, there's like references to other things and format arguments and so on. And the person was trying several different kind of like variations of simplifying things, having less. So this picture already looks a little bit simpler than this one at the top. So we went over simplifying things and so on, but in the end, this issue is still open. They couldn't get a lot of gains and things like that. So unfortunately is not something that you can just get the macro and just remove stuff. You just have to kind of like rethink how it should work. And because we have the benefit of working in a constraint environment, which is the VM, and you're writing a program, we don't have to include all sort of formatting things that we know that a program is not going to use. So we can start from a much simpler kind of like structure, because we know that, okay, let's just think of like what we want to format, and just include those things. So it's kind of like from the ground up already built with a simpler architecture, because we don't need to support all sorts of different things. But it still is usable, because you can even the log, there's a log trait. So even if you create your own struct and you want to say, I want this struct to be compatible with the log macro, and so you can format the strings with that struct, you can implement the log trait yourself, but it's a low-level trait. So you're going to have to really kind of like low-level implementation of how your type is going to be formatted. Then it's up to you to kind of like define exactly how to format your type. So in a way, it's kind of like is a simpler way to format things, but simplicity comes with a trade-off that anything complex, you're gonna either have to do yourself, or you're gonna have to try to simplify and print the information in a different way. And you can see even for simple things that doesn't involve a lot of formatting, because when you do a U64, you have to convert that number to a string. So there is some logic there to do that conversion. It's not simply, just put these bytes there, because you need to get the kind of like binary representation of the digits of the number. But even if you look at just concatenating a string, so you have message equal and then the message that you want to concatenate, even there, the MSG macro is going to charge you kind of like 440 for that formatting. And the log macro here is just uses 35 CUs. So even on simple things that is almost just copying the string into another string, you can do something simpler. Again, it involves a much simpler process, doesn't have all that kind of like architecture that I showed you on that link there. And arrays is something that is extremely expensive to log. So this is just kind of like an array of 32 bytes. And you see here that the cost of formatting an array on the SDK with the format macro is 7,000 CUs. On the log macro is still quite expensive, but it's kind of like roughly a third, no, more than a third cheaper to do on the with the log macro. So still there is gains there as well. And these are examples that the end result is exactly the same. So the message that gets printed is exactly the same. Doesn't have any difference. Okay. I'm a little bit conscious of the time, so I'm going to skip this demo, because this demo I can point you to the repo where is already there, so you can just run it in your own time. But essentially here there is a demo where it shows these three things here. It shows the gains on the entry point, the gains on the CPI, and the gains on the log. But I have a repo that have those examples already there. So I think this demo I'm going to skip. If we have time, I can go back and we can talk about them with the code. But I think it's going to be more interesting to jump into the P token and P memo before we go there. Unless someone strongly objects, let me know. All right. So so this part here. So those are the three main aspects that using Pinocchio you can really kind of like save CUs, and that probably is going to save you the I don't know 2/3 of the CUs just using those three things that I mentioned. But let's talk about some like now concrete examples to understand exactly the sort of gains that you could expect when you write a program with Pinocchio, and all the little tricks that you can also include. So P-token, if you haven't heard about it, is the reimplementation of this SPL token using Pinocchio. And it started with the goal of decreasing the CUs used by the SPL token. Right now, every block in Solana includes about 8 to 15% of the block is token instructions. So if you look at any block on Solana, let's say roughly 15% of the block is going to be the CUs of the block is going to be used by token instructions. So the hypothesis that we started was that, well, if we decrease the number of CUs, significantly decrease the number of CUs used by the SPL token, immediately we can create more block space. Because if 15% of the block is filled with token instructions, if we then make the token program use 2% of what it uses today, we then free up more than 10% of block space for any other instruction to be executed. So you can pack more instructions in the blocks because less space of the block, less CUs of the block are going to be used by the SPL token. And this then, it turned out that we managed to do that, and now is a CMD, is a 266, which eventually is going to be activated, and then we're going to replace the current implementation of the token program with P token and essentially create more block space because the token program is going to use less space. So how much we managed to reduce? So the P token essentially uses from 1.6 to 11.2 CUs of the current token program. So in the worst case scenario here, we reduce for like 88% of the CUs of the token program. But if you look at the top instruction, because the other analysis that we did is that about 90% of the token instructions are kind of like, about 50% of the all token instructions is transfers. And then the other ones is kind of like initialize account, close account, kind of like, I think, sync native and so on. But in overall, the ones that take 11% is kind of like initialize multi-sig, for instance, is an expensive one and so on. But those are not the ones that are so popular. So on overall, we are saving 12% of block space. If we replace the current implementation with P token, it means that we can create 12% of block space without having to change anything apart from changing the program. And this, obviously, what we did is that we re-implemented the SPL token program using Pinocchio, and it conforms to a binary level to SPL token. So the same account layout, instruction layout, everything. And we run tests, we run fuzzing, and it behaves exactly the same. So you pass the same instruction to either of the programs, and they're going to give you exactly the same state afterwards. So we managed to significantly improve the CU consumption, especially if you look at kind of like transfer, is like uses just 1.6 of the current CUs. Some other ones, sync native, thorn, revoke, set authority, those are also quite popular as well. So they are roughly around 3-4%. Some of them are, there is some things that you can't really optimize a lot. So the multi-sig is because you pass many accounts and they have to validate those accounts. So this is why like the reduction is a little bit smaller, because that instruction on itself is already doing more things. But for the very simple instructions, the reduction is it tend to be around like at least 4%. As a side effect of this reduction of CUs is there's a reduction of the binary size, because as I said, if you reduce CUs, it means that you're probably doing less things, which means a smaller binary. Some take-home points on this kind of like exercise of rewriting a program. About 70% of this reduction was achieved simply by changing the program entry point and using zero copy data. So just doing those two things, you already can expect roughly 70% CU. So if you got a program today, let's say written with the SDK using Borscht, and it takes 1,000 CUs, if you switch to use Pinocchio, use the Pinocchio entry point, and switch to use zero copy for your account access, data access, you should expect your program to then use around 300 CUs, from 1,000 to 300. That should be just those two simple things. Well, I say simple, but it's kind of those two direct things. There is no other kind of hidden things. So if you do those things, change the program entry point and change the account data, you should expect that. The remaining 30% then is tinkering. Then there is no really kind of like a clear rule how to get there. And many of the things that we did to go to this level of the optimization is that we had to do some unsafe Rust. Why? Because Rust is a safe language. So when you index an array and things like that, it includes automatically bounds checks. And sometimes the compiler can get rid of the bounds check, especially if you are indexing a static array with a static offset. So the compiler can determine that, okay, this index is valid for this array because the compiler has access to the length of the array and the length and the offset that you are looking. So then it doesn't include the bounds check. But when you are doing something that you got an array from the account date and so on, the compiler doesn't have that information. It doesn't know at compile time exactly what is the length of that array. So then it's going to include those runtime bounds check. And everything that you do in a program is going to involve executing a BPF instruction. So all those bound checks eventually get translated to a BPF instruction, which then adds up to your CUs. But if, for instance, you're writing a program and you validated that you got your token account, and you know that your token account has 165 bytes length, and you want to index the offset 100, when you're writing the program, you know that that index is going to be valid. As long as your account was validated to be a token account, you know that that index is going to be valid. Therefore, you don't really need Rust to do the bounds check, because your logic is already validated that that's always going to be true. So that scenario, you can say, you know what, I'm going to use unsafe here to not do the bounds check. So this is why, this is what I mean by tinkering. So you have to use a little bit of your domain to then be able to say to the compiler, look, you don't have to do extra things here because I know that this is safe. So if you go through the code of ptoken, you're going to see lots of unsafe, but every unsafe then has a safety note to say why that is safe to do. And the reason that we did that is that because then you can get those extra 30% of optimizations. You can start saving a little bit extra, but that is kind of, I would say, that is the last step on your optimization process. So if you have a program and you want to optimize it, the first thing that you should do is just switch to a efficient entry point, switch to using zero copy, and then if still you want to extract a little bit more optimization, then you go look at parts that you can say, well, here I can do some unsafe, and I'm going to save a little bit more. The level of what using unsafe gets you in terms of savings is in the order of kind of like 10 CUs, something like that. Is in the order of like 10s, 20, things like that. On the entry point and zero copy, you are talking about thousands. You can easily save thousands there. Using unsafe Rust is not going to save you thousands. Like, that's not going to the level. Even saving 100 is probably not likely. You're going to be able to, like a few CUs, you're going to be able to save there. There is many other things you can do before that. So is a little bit kind of like it's a trade-off. You might not need it to do, and so on. But it's just so for you to understand a little bit more what we mean by tinkering is going to those cases where you use kind of like domain knowledge of your program to then tell the compiler to say, okay, don't do these things. Sorry, there's another thing here on the chat. We are just avoiding runtime bounds check by precisely calculating how our program is going to be in compile time. Yes, essentially, so what you're doing is, so as I mentioned, Rust, because it's a safe language, is going to do bounds check when you're manipulating arrays. The compiler sometimes can get rid of them if at compile time it knows the length and can validate that that offset is valid. But if not, it's going to include instructions to do it at runtime. So by using unsafe, you are telling the compiler, trust me, don't include those things. So then when your binary is generated, there's not going to be those checks there. So that means less CUs. The danger is that if that assumption is not correct, then your program is going to panic, or it could be undefined behavior and so on. So you have to be careful at the same time. This is why it's unsafe. you need to be really careful that you can only include these unsafes for situations that you can, in one way or another, validate that it's going to be true. So I gave you the example of the token account. Is as soon as you validate that you have a valid token account, which usually tends to either you did a pub key validation or you did an owner validation with a length validation or something like that. As soon as you did that, you kind of say, okay, I know that this token account has this size, is guaranteed. So any indexing to that account data up to the size of a valid token account can be done with unsafe because you already validated that you have a valid token account. So it has to be used carefully, but essentially means that you simply tell the compiler, don't worry, trust me, don't include those checks on my binary. And then the compilation then gets rid of them. Okay, there's two aspects, two more things that we did on the P token, which also helped in make it more efficient. So the first one is we created a fast path for transfer instructions, because transfer instructions basically is half of all the instructions that the token program executes. So this idea of the fast path was in collaboration with KV. If people follow Twitter, probably saw KV works at Temporal, and he always give really good hints and tips for optimizations. So it's something that we work together, and he had this idea. Oh, let's do this fast path for transfer, because then we can even bring it down the transfer CUs. And the core idea here is to have a custom entry point. So don't use directly the Pinocchio entry point. Even before that entry point, do a custom logic where we give priority to transfer instructions, which essentially means we try to directly look at the input to see whether we are dealing with a transfer instruction. And if we are dealing with a transfer instruction, then we get the account and then call the transfer directly. So it doesn't go through the normal logic of the entry point. When we determine that is not a transfer instruction, then we fall back to the normal Pinocchio entry point, and we go through the normal entry point instruction. Because you can't do a fast path for many instructions, because then you end up in the same scenario of having your normal entry point. So the fast path you can do for a couple of instructions, because the more things that you do, then the more CUs you're going to be using, and then eventually you might end up in the same situation as if you were before. So fast path is usually kind of like is to give priority to a very small subset of instructions. But so it works very well on the transfer, because we determined that half of the instructions executed on the token program are transfers, and transfers is only 2 instructions out of the 25, 24 that the token program has. Those are kind of like much quicker to do, so this is kind of like the gains that you can get using a fast path, and it is something. So it's something that you could use in your own program if eventually you determine that there is one instruction or just 2 instructions, maybe, or 3 instructions that are more used than others. So if you determine that that is the case, then it's something that you can really kind of like use it efficiently to improve, because this way you literally in less than kind of like 10 CUs, you probably already determined that the instruction that you want to execute, and then you can just call that instruction directly without having to parse kind of like the whole input in order to determine what instruction is. So that is something that is something to keep in mind when you are kind of like hyper optimizing your program. The second thing that the ptoken has, which is new, is a batch instruction. So this is something, again, with collaboration with Dean Little this time from Blue Shift. This idea is that most of the time that you are interacting with the token program, you are doing multiple instructions. So sometimes you're just doing transfer, that is fine. But even if you think about a swap program, the swap program is actually kind of like is going to do a swap. It's going to do at least 2 transfers because you're swapping one token for another, so it has to do 2 transfers. In other cases, you are doing kind of like an initialize account, you are doing a transfer and closing account. So if you are sort of kind of moving funds from one account to the other, or from a vault. So if you think about a scroll program, from a vault to your withdrawings from the vault to an account, what is going to happen is going to initialize the account that is the destination, is going to make the transfer from the vault to that account, and then potentially close the vault account because the vault now is empty. So those are like 3 instructions already. And if you do that on a CPI, each CPI at least is going to cost you 1,000 CUs because that's the base cost, plus all the other little overheads that we discussed earlier. So that is kind of like, for most use cases with the token program, that is going to be inefficient because it's a lot of CPUs. So the idea of the batch instruction is to have, or kind of like the name already suggests, is to bunch all these CPIs into a single instruction, which is this batch, and then do a single CPI to execute the whole batch in one go. So you pay the base cost just once, and then you can execute multiple instructions. That is something that we had them to come up with a way to encode this information into the instruction data and the account list in order to make it work. And the way that we did is essentially we kind of like concatenated the instruction data and the accounts used by each instructions. So we created a little bit of a header on the instruction data where it tells the number of accounts the instruction is going to use and the offset where the instruction data ends. Because with this offset, you can then get exactly the slice of instruction data for the first instruction. So now you know the number of accounts that this instruction is going to take. You know the slice of instruction data that the instruction takes. So with those 2 bits, you can get your accounts from the overall accounts array. You can get the slice of instruction data from the instruction data array and process one instruction. And then you go to the next, get the number of accounts of the next, the instruction data offset of the next instruction. Then you get the accounts for the second instruction. Here, there's a little bit mistake here on my drawing. It should be up to here. Let's follow the color. So the color is more accurate. So will be the accounts of the second instruction, and then the instruction data for the second instruction, and so on. So you can append as much as you can. Obviously, you still have to respect the limitation of the sizes for the instruction data and account. But as long as you can fit, you can easily fit here like 10 CPIs into a single one. Those limits are much higher when you're doing CPI than when you're calling from the outside off chain to on chain. When you're doing a CPI, the instruction data limit is much higher. So here you can concatenate, and then what happens is that you pay these once because you just send these once to the program, and then the program iterates over this data, slicing it identifying the individual instructions and executing them inside a single execution of the program. So that, like, immediately, if you think about this simple example here, very rough estimate, instead of paying 3,000 CUs to do 3 CPIs, you're going to pay 1,000 CU to do those 3 instructions. So immediately you save 200 CUs. And the more instructions that you want to execute, the more CUs you're going to save. So if you were like 7 CPIs that you're using, immediately you can reduce that 7,000 CUs to 1,000 CUs. So immediately you save 6,000 CUs. So he's asking here whether if there is any cases where it might not work. We didn't come with any edge cases. What you need to be more conscious is about security. And I think the next slide is the demo. So let me just, let's open here the repository. This programs token. I'm going to open the repository because you need to be more security mindful for the batch. So let's look at the batch first. So on the token repo, if you go under the Solana program token, the program is the current program. So this is the SPL token implementation. The Pinocchio implementation is kind of like intuitively under the Pinocchio folder, and then you have the program. So here is the P token. We're going to go to the processor, and then we're going to look at the batch. So here is essentially what I was mentioning to you. Is very. Let me just put this a little bit bigger. Let me know if if you can't see the writing. But as I mentioned, that in the instruction data we have these 2 bytes of header, which the first one is the expected number of accounts. The second one is the offset of the data. Just on a sidetrack here, this is a good example of an unsafe that we are using here with our safety note here. Why is it okay to use the unsafe here? Because we already validated that the instruction data length has at least 2 bytes. So then we can say, okay, we're going to index those 2 bytes directly now. I don't need bounce check here again, because I already did the manual validation of the length. So this is a clear case where you can use unsafe. It's gonna save you 1 CU. It's not gonna save you a lot, but like add up. So this 1 CU for each unsafe here becomes 2 CUs. So this is kind of like the tinkering that I was mentioning. It's kind of like, because I already validated something, I already can figure out that this is correct. This is not gonna fail. So you get those two bytes there for your input. There is a bit more validation here to see that the offset for the data is valid, because now we are checking, does the instruction data is long enough up to that offset that it was informed in the instruction data? Does the accounts list still has enough accounts for these instructions? So there are a bit more validation. And then again, because we did some validation there, we can do some unsafe here to get exactly the slices that we need from the accounts and the instruction data arrays. We then determine what instruction is being called. And here there is a note, which is the caveat of doing things in batch. Because what happens with the token program, some of the ownership checks are done implicitly. So it means that I'm writing to an account, so I must be the owner. So I don't need to do the owner check. But obviously, when you're doing that in batch, that ownership check only happens at the end of the instruction. So you might end up executing multiple instructions until you determine, oh, actually, that account, I shouldn't have modified it. And that obviously creates a problem, a security problem in this case for the batch. So what we had to do here is include extra validation just for the batch scenario. So we determine which instruction we are executing, and then we do some owner checks here because the individual instruction is not doing them because it's optimizing the checks. But on the batch, then we need to do it. So that kind of like is a really good question on the chat. The edge cases, yes, there are edge cases that you need to be aware. And you might need to include extra checks on your batch or modify your original instruction to make sure that it works in batch. So either way, but it does have edge cases there that you need to be aware, because if you rely on anything that the runtimes enforces at the end of each execution of an instruction, when you're doing them in batch, those runtimes are not gonna execute. They're gonna execute at the end of the batch. So you're gonna execute several instructions before the runtime does their checks, its checks. So you need to be aware. So here, if you look at the code here, you're gonna see that, yeah, we had to do some owner checks here. After that, then essentially we just call our normal processor implementation with that instruction data and that accounts. From that perspective, the instruction doesn't know that it's being executed in batch. The instruction just execute as if it was any other execution. And after we execute that, we update our references for the accounts and instruction data. So essentially, we consume the values that we already use, and then this loops to the next. So all of this is inside a loop until we consume the whole input, which is the accounts and the instruction. So if you think that like the batch implementation is just this, like there is no other outside magic necessary to implement a batch instruction, is essentially this. It's a very simple implementation. But obviously caveats definitely have to be there. The second thing that I wanted to show you is just very quickly the fast path implementation. So this is on the entry point. So the entry point here, you see that we actually manually created an entry point here, which is this unsafe function. We pre-computed all the offsets where things would be if we were dealing with a transfer instruction. So those are all pre-computed offsets. And then essentially we go and say, okay, if I have 4 accounts, because that's what a transfer check takes. If I have 4 accounts, that means it could be a transfer check. Then we're gonna offset in each of the accounts to check the data length, because we know that the first account has to be a token account, so 165. The second has to be a mint, so 82. The third has to be the destination, 165. The fourth, we don't care, it just has to be an account. So we validate all these things before, and if those things are all correct, it means that, okay, potentially we are dealing with a transfer. Then we eventually calculate where the instruction discriminator is gonna be, and then we read that, and then we say, okay, is it the transfer check discriminator? It is. So then we grab all the accounts, and then we call here. We do the same thing for the transfer, because if it's not 4 accounts, it will be 3 accounts, and then we're doing a simple transfer. And similar checks here to see whether the accounts are potentially for a transfer. Again, we go eventually calculate and jump exactly where the discriminator is. So we check, okay, transfer is here. It is a transfer, and if it is, then we grab the account, and then we go and call the transfer directly. Now, if all of this fails, then we simply revert back to the Pinocchio entry point implementation, which calls this deserialize function, which this is a Pinocchio function that parses the input for you. So then basically we revert to the normal one, and we continue. So this gives priority to the transfers, with the trade-off that you add a little bit overhead for all the other ones, because you had to do some checks before. There's another question here on the chat. Are those predefined precondition values never really? Yes, on the input buffer. So the input buffer. If we go back, let me just go back here very quickly. So if you remember this slide here, so the number of accounts is always the first position, and then you have your accounts, and at some point you're going to have the length of the instruction data, and so on. The problem is that you don't have the length of this input, so you can't offset things from kind of like from the back to the front, and this is why we need to kind of like check first the number of accounts, which is what we do here, and then we assume, okay, do I have this account here? Do I have this other account, and so on? So the offset is the expected offset of where they are going to be. The fact that I have 4 accounts makes this offset valid, because I know that there are going to be 4 accounts, and the accounts they have those paddings and everything. Like 10K paddings and so on. So those offsets are always going to be valid, regardless, because I might have had a shorter account. So I might have this second account maybe was shorter, but then this condition is going to fail, and then I'm not going to try to then continue reading and end up with an invalid offset. So if you do them all in sequence, you're always going to end up with valid offsets as well. But yes, they are all pre-computed here, the expected offset. So here we actually put kind of like all the offsets. If there were actually a transfer instruction, they will be in that position. If something is not in that position, it means that it's not a transfer instruction. And then we simply revert and then go back to the normal entry point. So again, I would say it's not a super complicated change on the implementation, but it gives you some good gains for your most used instruction. So I would consider, for a scenario where you have 1 or 2 highly used instructions on your program, this is going to be beneficial to do. But that's, again, that is kind of like at the low end of the optimizations. That there are other things that you should do first that is going to give you the big chunks of optimization. This is this categorized on the tinkering side. This is another tinkering. Is the unsafe? Is this and so on? Those are the tinkering kind of improvements that you can do. Okay, so this was P-token. The other one that we did was a reimplementation, the SPL memo using Pinocchio. Memo is a very simple program, but also surprisingly one that uses a lot of CUs in relation to how simple the program is. And it's quite used as well. If you track the memo program, there is going to be multiple transactions for involving memo, kind of like in blocks, in every second, basically. So the idea there is to reduce the use. It's not as used as the token program, but is quite used as well. And so we were like, okay, well, we can re-implement the memo program as well. And that was a good case for a lazy program entry point, because the memo is a single instruction, doesn't have an instruction discriminator. It does just one thing: logs a message, and then could include optionally a list of signers. This is essentially what the memo does. So the implementation, what we did is that we use the lazy program entry point, because we don't need to parse the input nicely, because we don't need the instruction data separate from the accounts and so on. No, we can do that on demand. It's going to be cheaper. We use the syscall to format the pub key values on the log, which is much cheaper than formatting a pub key on a program, which is what the current memo does. And we also use the Pinocchio, the log macro with the log syscall to then format the memo message as well, because it prints the memo message to the log. So we also do that as well. The gains here are kind of like relatively similar to what we got when we were doing the P token. You see here that for when there are no signer presents, the gains are smaller because the only thing that the program is going to do is the log a message, and log a message is limiting how much you can improve. Although we managed to basically reduce to just use 15% of what the current memo program does. So a memo program with this, I forgot to write here, but this is with a 64 bytes memo message. So memo program just logging a 64 bytes message is going to cost you 2,000 CUs. With the reimplementation, it goes down to 313. If you include signers, then the gains are even more significant, because what happens is that you have then to parse accounts. So then your entry point is starting to consume more CUs. And then you have to then check whether the account is a signer or not and log the signer pub key. So then you can see with a memo, with a 64 bytes message and 3 signers is gonna cost you 36,000 CUs. If you use the reimplementation, it costs you 771. So it uses basically 2% of the current. And then this kind of like, if you keep increasing the number of signers, then the improvements here are going to be tending to 0, basically. Never going to reach 0, but you're going to probably reach a point where it's going to be using 1% of what the memo program uses and so on. So the percentage here is going to just be going down, down, down as you increase the number of signers. So I just wanted to very quickly then show you here the memo program. So again, everything lives here on the Solana program organization. So if we go to memo, it's going to be there. Intuitively, it's going to be a folder called Pinocchio that is going to have the implementation. This one is even simpler, the implementation. So the lib here is just the declaration of the lazy program entry point. And then if we look at the entry point, this is the whole implementation of the memo. You can see here that is using the instruction context that I mentioned from the lazy entry point. So you don't get a list of accounts, a list of instruction data, but you do get is an API where you can query what is available. So first we check whether there are remaining accounts. If there are remaining accounts, it means we have signers. So it's gonna log to say that, oh, there is signers. It's gonna loop through all the signer available. So all the accounts that are available. It's gonna get the accounts one by one. So this is parsing on demand, checking that it is a signer, and then log using the syscall. It barks if there is any missing signer, like the original memo program. Then after we process all the accounts, then it's safe to go and get the instruction data from our input. So we get the instruction data. We use the log here to log what's the length of the message. This is something that the original memo program does as well. And then we log the message using the syscall, and that's it. So this is how kind of like what the program does, and like the use of Pinocchio here to save CUs. So yeah, this one is obviously simpler because the program does one thing. So the lazy program entry point is ideal for cases like that, where your program does one thing. So if it does one thing, you don't need this whole sophistication of the entry point. That entry point is more suitable for programs that execute multiple instructions. So you don't know exactly how many accounts you are getting and so on. For programs that are very simple, like the memo, the lazy program entry point is going to be more efficient, because then you can control exactly what to parse, when to parse, and so on. So you can do this stuff on demand, and then you're gonna end up using less CUs than the standard one. Okay. So as I promised at the end, because I think I had 2 minutes to wrap it up, I think timing was perfect. Jumping the other demo wouldn't have had time, fortunately. But the other demo, what I was going to do, I was just going to show you this this repo here. Let me just open up very quickly. Here. So if you go to the link here, this is essentially a very simple repo with a playground where there is a Pinocchio program and there is an SDK program. There is some benches already set up, and then you can execute benches for the entry point, benches for the CPI, and benches for the log. So these are the results with the Pinocchio, but you also can run the same thing with the SDK, and then you can see all the differences. But those are the values that I kind of like show you on the slides. And then here you can also use this to test any other change. So you can go on the program here, and then go on the Pinocchio or SDK. You go on the entry point, and then you can change the implementation of the process instruction and just run the bench again, and it's going to measure the CUs. The other things that I added here is the link for the Pinocchio repo. If people are not familiar with Pinocchio, they can check it out there. There is more explanation on the README of the repo and everything. This is the playground that I just showed you. pToken and pMemo is the one that I just, we went through the code a little bit. And yeah, I think I just wrapped it up exactly on time. I don't know if there is questions or there is any time for questions as well. But yep, happy to answer anything. Well, the thing is that the SPL is that we need to replace the implementation on the program. So there is a question why programs are still using SPL. Sorry, this is the library. Okay, the SDK you mean? I think you meant SPL is Solana program library, but I presume that you mentioned you're meaning the SDK. We are in a process of kind of like integrating and in a way Pinocchio-fy the SDK. So soon you're going to be using things more efficient from the SDK directly. So I can show you very quickly here. If you look here, there's some new crates. Some of them are still not published because I'm in the process of publishing things, literally this week. The account view is actually the account info from Pinocchio, but with a different name. So this is literally what I showed you there. If you remember this slide, when I showed you the account info from Pinocchio, there was just a raw pointer. Now that is becoming an SDK type called account view. So then you're going to have a Pinocchio entry point using the account view. The other thing that I mentioned to you about CPI being more efficient, there is now an instruction view. Oh, the instruction view is still APR. Oh, it's still APR. Probably under review. Yeah. Okay. This one is still not merged, but it's there. So the instruction implementation from Pinocchio is becoming the instruction view in the SDK. So as I said, we are Pinocchio-fying the SDK. So the Pinocchio entry point eventually is going to use SDK types. And then if you go to the Pinocchio repo, there is an issue there that you can track all the changes. Here. So we have here, so this is sort of like already just waiting for us to finish the changes on the SDK, and then all this PR eventually is gonna go in, and then they are gonna be sort of using the same types. So eventually people are gonna be using all these, improvement. So that's the plan, essentially, is to Pinocchioify the SDK. So all these things that we learned by doing Pinocchio, we are bringing to the SDK as well. So then we cannot do much on the entry point, because the entry point will be kind of like, you have to write a new entry point. So there is going to be 2 entry points. But as long as you use the more efficient entry point, then you're going to get all the benefits of these efficiencies later. So soon enough, I think everybody's going to eventually be using efficient types for programs. But this is why I do recommend people that want to kind of like dig in a little bit more and kind of like understand a little bit more how these things actually work. I do recommend going through these links here. We try to add all the information there, even in the code, the comments and everything. As I said, on ptoken, every use of unsafe, there is a safety documentation on top. So then you can understand exactly why it's safe to do that and so on. So people that really want to dig and kind of like get the nitty-gritty details of things, I think these repos is going to be the best resource. Just wondering why Anchor did not. So if there's any trade-off in using zero copy accounts, there is. I think it's more on the DevEx side. Is a little bit. I don't want to use the word complicated, but I can't think a better word on this spot. But it requires a little bit more understanding of kind of like lifetimes, and you have to work with referencing. You need to understand type alignment and things like that. So it's not something that is very easy to make it work out of the box with a single line. So when you use Borscht and so on, then it's kind of like, it's easier, because Borscht, you don't have to worry about these things, because it's just going to copy all the data for you and everything. So you don't have to worry about references, lifetimes, alignment, and so on. So I think it's a little bit more kind of like, in terms of DevEx, it's easier to use something like Borscht than zero copy. But I would argue that once you use zero copy once and understand, then there is no overhead in using zero copy the next time. The first overhead is the first time that you're using. So there is a learning curve there. So it's kind of like, yeah, it's more, I would say it's more to do with DevEx. What is easier to get out of the box and running something quickly? You need, if you're more experienced, you're probably going to find out there's no difference. I can do zero copy. But if you are learning and then you have to learn zero copy on top of it, you're like, oh, wow, all these things. So I think it's a little bit that. Although Anchor allows you to use zero copy as well. There is an account loader in Anchor, which essentially you can write zero copy types with Anchor as well. So it's possible. But as I said, it's not as automatic.